Okay, now let's talk about kernelized logistic regression. So basically, this is a way of avoiding an explicit feature definition. But we are still going to make a sort of an arbitrary choice in our implicit definition. But let's see how this comes about. So let's talk about first what is called the kernel trick. So that's goes sort of beyond logistic regression. It's true for pretty much any regression. So basically, suppose your decision or whatever you want to do is based on some linear function of some feature vector phi, right? So this is what my decision is based on. This could be regression, classification, whatever. And as usual, you're given data points x1 through xn, and you have phi I, which is the feature vector corresponding to the ith point, right? So this means that your training is based on these numbers, W transpose phi 1 through W transpose phi n. You don't really have anything else to go by. Because your decision is based on W transpose phi of x, that's what your cost function is going to be based on. So the training is based on only these numbers, right? And how they evolve as you change W. So, any component of W orthogonal to all of these guys, to phi 1 through phi n, is irrelevant because it doesn't contribute anything towards these numbers, and hence it cannot contribute anything towards the training. Which means that we can take, without loss of generality, we can take W to be just a linear combination of these feature vectors corresponding to the training sample. So there's no loss of generality in doing that, because any component orthogonal to it, we don't even see it. And of course, I can write it compactly as the product of a matrix phi and a vector A, where the matrix phi has these feature vectors as columns, and the vector A is a column vector of these coefficients with which we are combining these feature vectors. So basically, these guys are D cross 1, so this matrix is D cross n, and this is an n cross 1 vector, so the product is this W, which is D cross 1. So once we do this, let's go back and look at what the output or the decision variable is for a generic feature vector for any generic data point, whether it's during training or during inference, right? So I'm just going to plug in W here. So that's W transpose is phi A transpose, and then I'm multiplying it by some phi x, and that's A transpose phi transpose phi x. So what is this? It's basically just I'll just write it summation j equals 1 to n aj phi j transpose phi x, going back to, let me change my pen color, going back to this representation. All I'm doing is taking the inner product between these training feature vectors and some other feature vector phi x, whether it's for training or inference. That's what I'm doing, right? And then of course I can compactly write it in this form, right, as A transpose phi x. So what we have shown now is that the decision variable depends only on the inner product of these feature vectors corresponding to training and any other feature vector that you bring in, right? So basically, instead of specifying the feature vector phi of x for any data point x, it is enough, it suffices to just specify the inner product phi x transpose phi x prime for any x prime, right? So then if you knew that, then you could basically find the inner product between any two training feature vectors as well as the training feature vectors and any new feature vector corresponding to a point that you want to do inference on. And at this point, we can get all abstract and basically say, actually, I don't really need to know what these guys are. The inner product is a very generic notion. And all I'll tell you is some function that given two data points gives me their inner product. And now I'm going to denote the inner product in this fashion. Phi x prime, right? As long as I have a function that tells me for any two data points their inner product, I can do both my training and my inference. And this is what is called the kernel trick. So this guy, this kx prime is called a kernel. And as long as you tell me how to compute this inner product, I don't really need to tell you what those feature vectors are. And this is what the kernel trick is. So what are some example kernels? A very, very popular kernel is the radial basis function kernel. So basically kx prime is of this form. You basically have x minus x prime squared divided by 2, kind of looks like a Gaussian. You want to give it the opportunity to vary with depending on how fast you want to vary around the point you are at. You have a length parameter L, and of course you see here that kxx is equal to 1, and the picture looks like if I'm at an x, and I can't draw a multi-dimensional picture, but basically it's like a Gaussian distribution around it, and how fast it varies depends on this hyperparameter, sort of the length parameter L, and of course this is positive. And the bigger you choose L, the more of a spread you allow, and the smaller you choose L, the more tightly concentrated you are around the point X. And you can see that this kernel is implicitly coding very high dimensional terms. So if you expand this out, kx prime for this radial basis function kernel looks like, okay, there's one term like this. When I just expand out that norm squared term, there's one term like this, there's one term like that, sort of the energies of these vectors. We can even think of them as equal energy now. And there is an inner product between the original data points, x prime divided by L squared. So instead of actually having just an inner product between these guys, you have the exponent of the inner product. And of course, you know that e to the a looks like 1 plus a square over 2 factorial plus a cubed over 3 factorial, etc. So you can see that essentially you have very sort of high dimensional quantities, high dimensional powers of these x's and x and x prime products, right? Basically, if I have x prime, that inner product, that looks like, I equals, or let me call it k equals 1 to d xk x prime k. So that's the inner product. And now you're taking these to the power of, if you're taking this to the power of M, you see that all sorts of higher order terms in the x's and x primes come into the picture. So you're implicitly encoding a lot of nonlinearity when you are specifying this kernel, and of course you're weighting the higher order nonlinearities in different ways, right? The a cubed term here is weighted down by 3 factorial, and the a 10th term is weighted down by 10 factorial. So you are preventing things from blowing up, but you are allowing a lot of freedom in terms of what kind of functions you can represent. Another kernel that you can use if you're just interested in polynomial terms up to a certain degree is, for example, x prime equals, I'll just take that inner product x prime, and I'll allow myself to raise it to the power, some power. And generally speaking, I add a constant to it also, so that I have all the other powers in there, right? All the lower powers in there. So when I expand this out, I'll have a bunch of other powers. So in all these cases, the free parameters that I'm putting in, like the length parameter for the radial basis function and this parameter a and m, there's a bunch of hyperparameters that you will need to play with. We should also introduce some notation. Often you're taking these inner products via just this kernel computation of a bunch of different vectors. So so this is sort of a notation that I have in the notes too, that essentially if I'm taking the inner product between two sets of potentially different data points. So this might have a certain number of data points. Suppose these are m data points, and this might be n data points. What I have here is the ijth entry is the kx I x prime j, where xi is the ith point in xa, and xj prime is the jth point in xb, and then this is a matrix. It's an m cross n matrix of all these inner products between those data points. So for example, we'll often have if I say that my training data x is I have basically the capital N data points, and then sort of k x is an n cross n matrix where the ijth entry is phi xi phi xj, right? Except that you're not actually computing it, you are just explicitly via features, you're just doing it using the kernel. So we'll use this notation quite a bit. And the last general observation about the kernel trick is the positive definiteness condition. So not any function of 2 data points is a legitimate kernel. What the positive definiteness condition comes from the fact that if you give me a bunch of any number of feature vectors, phi1 to phi l, if you give me a bunch of feature vectors like that, then the matrix phi transpose phi is non-negative definite. That has why is that the case? That's the case because positive definiteness. What does that mean? It means that u transpose phi u has to be bigger than or equal to 0 for any vector u, and by you can actually see that this is just phi u transpose phi u, which is just the norm squared of phi u, which is guaranteed to be positive. So any matrix of inner products has to be positive definite. So this is This is just the notation for positive definite, right? Or non-negative definite. So what does the kernel give you? The kernel gives you, that phi transpose phi looks like K XA, right? Basically, I'm taking an inner product between feature vectors corresponding to the same set of data points, and this is the matrix. And what we need is this should be positive definite for any choice of data points, right? And that's what positive definiteness for a kernel means. And both the kernels we have talked about are positive definite. You can show that, but we are not going to show it here. I would leave it to you to sort of dig it up in the just do an online search or think about it yourself and show that these kernels that we talked about are positive definite. So